Magnesium is the lightest structural metal. Magnesium-based alloys attract attention in industrial application for its lightweight, high specific strength, and good castability. It usually includes magnesium, aluminum, zinc, and etc. It is commonly used in automobile and aerospace industrial as material for structural parts. Among all processing methods, high-pressure die casting is the current dominating processing method for magnesium alloys because of its faster prototyping speed, better casting dimensional accuracy, and less post-processing request. A most common cast magnesium alloy is AM series alloys, containing 47% aluminum, less than 1% manganese, zinc, and silicon, which is explored in this project. During the high-pressure die casting process, after superheated metal is firstly poured into a shot chamber, solidification happens. Crystals nucleate and grow at this time and become externally solidified crystals, known as ESCs. Other microstructures, including ARF magnesium-rich grains, bad aluminum magnesium facies, porosity, and defect bands, also form as a result of solidification. In this project, we will focus on ESC structures, which appears as large, bright dendrite-form faces. The variations of mechanical properties have been found to be depend on alloy microstructures, such as porosity, oxide skin, and grain size distribution. ESCs play a significant role affecting fatigue resistance, tensile strength, ductility, and so on. For example, in terms of hole patch model, since ESCs show a significant larger grain size comparing to fine ARF face grains, ESC would cause a remarkable increase of the average grain size and consequently should have a notable effect on alloy yield strength. It is the objective of this contribution to investigate a quantitative conclusion for high-pressure die casting AM series alloy ESC's spatial and size distributions. Such distribution was applied to modified hole patch model to quantify its ESC's effect on yield strength, and would be further used to predict other mechanical properties for magnesium alloy. The raw material was firstly sectioned to sample slices on autosaw. The slices were mounted to be sample biscuits using epoxy. The mounted samples were grinded and polished on auto polisher. The polished sample surface is etched using nitric acetic acid. The final step was to observe the sample surface on optical microscope. Microscopy images of sample surface will be collected. The collected sample pictures were processed in Photoshop and ImageJ software. A MATLAB simulation program was developed in this project in order to simulate the complex ESC microstructures from microscopy image to simple circle grains. The simulated ESC size and spatial coordinate were also analyzed in this MATLAB simulation program. With the analysis of data from MATLAB simulation, the variation of local ESC area fractions for different alloy compositions and thicknesses are shown below. Center region possesses an average of 0.188 or 0.157 ESC area fraction for 5.0 or 2.5 mm thickness alloy respectively, which is much higher than the edge region ESC area fraction. ESCs mostly appear in center region and rarely appear in edge region. This result is consistent with the direct observation from microscopy image. ESCs rarely appear as edge region. Finite edge region ESCs are all of a diameter smaller than 40 microns. For center region ESCs, their average diameters are mostly about 80 microns. Thicker alloy plates show a slightly higher average size than 2.5 mm plates for AM50 and 60, and possess same average size for AM40 and 70. 5.0 mm plates have an overall 2% larger average ESC size than 2.5 mm plates. For each composition and thickness, all recognized ESCs are classified to different size bins. For all alloys, ESCs with a diameter smaller than 100 microns covers about 40% of all ESC area. As the ESC diameter increases, the correspondent ESC area fraction decreases. For each sample thickness, curves of different compositions overlap each other, and for any certain size bin, there is no significant area fraction difference between different compositions. It is reasonable to conclude that alloy composition shows no significant effect on size distribution. In order to illustrate the plate thickness effect on size distribution, the ESC area fraction for different compositions were averaged to derive this figure. Thicker plates possesses more ESCs of diameter ranging from 250 to 350 micron, but less ESCs of smaller than 150 micron diameter. For ESCs with a diameter of 200 micron and larger than 400 microns, both thickness show same area fractions. In general, thicker plates possess more giant ESCs than thinner plates. In order to verify the validity of the MATLAB simulation result, a standard test method for determining volume fraction by systematic manual point counting ASTM E562 was performed on AM60 samples. According to the table, most of the MATLAB simulated area fractions show that they locate within the confidence interval of ASTM result, and hence are reliable. In hole patch strengthening theory, grain size has an effect on material yield strength because grain boundaries impede dislocation moment. The ESC distribution discussed above were applied in hole patch modeling here to evaluate the ESC's effect. For 2.5 mm samples, the modeled yield strength matched the experiment only for AM40 and 50. However, for 5.0 mm samples, only the model for AM60 and 70 matched the experiment result. The mismatch is highly possible because this model only takes grain size effect into consider, but does not count other effects, like porosity and solid solution strength. In the present investigation, alloy microstructure characterization and quantification have revealed the following for AM series alloys. ESCs usually appear in alloy center region and rarely appear at edge region. Alloy composition has no or very little effect on ESC distribution. Alloy plate thickness affects both size and spatial distribution. Thicker plates possess larger area fraction than thinner plates. At last, I wanna acknowledge that the investigation is instructed and advised by Professor John Allison and Dr. Tracy Berman. This work is jointly funded by Professor John Allison, Allison's group, and Shore Program, University of Michigan. I would also like to thank Aaron Data for instruction and support in yield strength modeling. Thank you very much.